Okay, in this video we'll look at electrostatic charging. Electrostatic charging, also known as electrification. So electrostatic charging or electrification is the process of making a material to obtain charges. The process of making a material to become charged is what we call electrostatic charging or electrification of an object. Now, it is important to understand where charges originate from before we proceed to look at further concepts of electrostatic charging and the methods of doing so. In our previous videos, we have looked at the modern picture of an atom. This is how it looks like. You have a nucleus, and inside the nucleus there are protons and neutrons. Neutrons have no charge, protons have a positive charge, so the net charge of the nucleus is positive. Then you have the energy levels. These are the energy levels, and so on these energy levels there are electrons. In fact, in the second picture you can see that these electrons form sort of an electron cloud around the nucleus, so the net charge here is negative because the electrons are negatively charged. Okay, so it's important to understand the atom before we proceed to understand how electrification takes place. So let's talk about the atom, or to be more specific, let's talk about atoms and ions. And basically an ion, I hope we all know what an atom is. An ion is a charged atom, and this is basically obtained by adding. Is this obtained? I should say this is formed after an atom has lost or gained electrons. So if an atom gains or loses electrons, then it becomes charged, and in that case we don't call it an atom, we call it an ion. We shall see under which case we call it a positive ion or a negative ion. Okay, let's move further. Just need to create more space here. Let's begin with what an atom looks like. So in a neutral atom, we know very well that inside our neutral atom here we have protons, and then we have electrons surrounding the proton. In a neutral atom, it is known that the number of protons is equivalent to the number of electrons. So since protons and electrons have an equal charge, if the number of protons is equal to the number of electrons, that basically means that the atom is electrically neutral. However, let us impose some conditions here. If the number of protons is greater than the number of electrons, then the atom has excess positive charge, and in that case we say it is positively charged, or we say it is a positive ion. So when does an atom become a positive ion? Basically, an atom becomes a positive ion. An atom becomes a positive ion after losing some of its electrons. If it loses some of its electrons, then the number of protons inside the nucleus will remain unaffected, so it does not counterbalance the now few remaining electrons. That makes the net charge on the atom to be positive, and so we call that a positive ion. Okay, let's look at the second scenario. If the number of protons is less than the number of electrons, that means the atom has excess negative charge. So in this case, it is called a negative ion, and this happens when, so this happens when an atom gains excess electrons, most probably from another atom. So if an atom gains excess electrons, it becomes a negative ion, and if it loses electrons, it becomes a positive ion. It's important to remember here, this is important, it's important here that ions are created or formed only by adding or subtracting electrons from an atom. The bottom line here is that the nucleus cannot be altered, at least with ease. So it cannot be altered because the nuclear forces that bind these protons inside the nucleus are very strong. It is almost impossible to alter the nucleus, but it's very easy to take off some of these electrons or to add more electrons to the atom to make it an ion. And so with this background in mind, we are now ready to understand what happens during electrification, because it all happens at atomic scales and it is manifested at a micro scale where the whole object becomes charged. So we have the methods of electrification. That we'll be looking at. The first method is going to be charging by rubbing, sometimes called by friction. Another method is going to be charging by contact, sometimes we say by conduction. And lastly, we are going to look at charging by induction. So let's begin with charging by rubbing. Let's create more space here. Charging by rubbing. So if we have two materials, and suppose two unlike, let me use a better word, if two dissimilar, that means the materials should not be the same. If two dissimilar materials are rubbed together, obviously if you rub two materials together, then there is going to be some heat energy generated. So heat energy is generated. Heat energy is generated due to friction. And because of the heat energy that is generated due to friction, the energy provides, or the energy enhances, the removal of electrons. The energy enhances the removal of electrons from one material to the other material. And basically what happens here is that the material that gains electrons, becomes, as we have seen for the case of the atoms, the material that gains electrons becomes negatively charged, since it has an excess negative charge, and the material that gains, the material that loses or donates electrons becomes positively charged, because it has few electrons remaining to counterbalance the positive nucleus, so it has a net positive charge and it remains positively charged. Let's illustrate this with the case of a glass rod. So assuming we have a glass rod which is originally neutral, and we have a piece of silk which is also neutral. If we bring these two objects together and try to rub them, if the piece of glass and the piece of silk, let me indicate the silk like this, if the piece of glass and the piece of silk are rubbed together, in the end, the glass rod is going to lose electrons, so it becomes positively charged, while the silk is going to gain the electrons, so it becomes negatively charged. It's important to note here that the electrons lost by the glass are acquired by the silk. So once again, the law of conservation of charge is obeyed here, because we have not created any new charge. We have simply transferred charge from the glass rod to the piece of silk. So this one here, we say it has lost electrons. It remains with a net positive charge. This one here, the piece of silk has gained electrons, so it has an excess number of electrons. Therefore, it is negatively charged. Now, the exact factors that lead or that determine which material loses or gains electrons are rather important to discuss. So we have about 3 factors that influence the loss of electrons, and these factors are basically the electronegativity, of the material or of the atom. Basically, electronegativity is the ability of an atom to attract shared electrons towards itself. So in the previous example of the glass and silk, it turns out that the silk is more electronegative, so it attracts all the electrons to itself, while the glass rod is more electropositive. Another factor here is electron affinity. The electron affinity, so this is, I could say, the love of electrons. Basically, objects with a high electron affinity tend to take all the electrons, so they become negatively charged, while the opponent becomes positively charged. And lastly, the work function. Maybe not last, but also we have the work function. So the work function is the energy required to remove a free electron from the surface, of a metal. Work function is mainly defined for metals, although we can also talk about work function for other materials. But in terms of electrostatics, work function could be a general term for all materials. In photoelectric theory, work function is very specific to metals. Okay, lastly we have ionization energy. And basically ionization energy is very similar to work function, only that with ionization energy we are not taking free electrons, but we are taking the loosely bound electron from an atom. So basically with these two, work function and ionization energy, the smaller the work function or ionization energy, the easier it is for the material to lose electrons. So this method, the method of, let me clear the screen, the method of charging by rubbing is ideal or very common, is ideal for insulating materials. However, conductors can also be charged by this method. Conductors can also be charged by this method, provided they are well insulated and isolated from the earth, which may take away or add electrons to them. Okay, I'll finish this by showing you a simple table here. This table here shows something called Okay, so in this table shows something called the triboelectric series. And basically this is a series that determines who loses electrons and who gains electrons. In this table, as we go up, we can see that there is more tendency to gain positive charge, so these guys lose electrons as we go up, and as we go down, these guys tend to gain electrons because they have a high electronegativity. So if you take an example like silicon rubber, which is at the bottom of the group, and you rub it with asbestos, it is most likely that the silicon rubber will become negative and the asbestos will become positive. Ideally, we always rub materials on top of this list with materials at the bottom of the list to get a better experience of what charging looks like. We always get a combination of materials on top with materials at the bottom. That gives us a better experience when charging. The word triboelectric comes from, it's actually another word to mean frictional electricity. And by the way, the method of charging by rubbing is also called the triboelectric method. So this term shouldn't be that bad. So be sure to pause the video and look through this list. Perhaps I need to make it bigger. Look through this list to determine which materials should be rubbed with other materials and which kinds of charges are generated. Okay, let us now proceed to another method. Before we proceed to another method of charging, it is important to note here, that when insulators are charged by rubbing, the charges only exist at the surface, because these materials basically are insulators. They cannot transmit charge inside. For example, if a piece of glass is rubbed against human hair, let's assume the piece of glass gains positive charges. These positive charges will only reside on the surface, not inside the material of the glass, but rather outside the surface, because this is an insulator. The charges cannot distribute themselves inside. Okay, basically also the negative charges on the hair will reside on the surface. So that's very important to note for charging by rubbing, especially for insulators. Let us now look at another method of electrification, and that is charging by contact. So this basically is a method. This is a method commonly used. It's a method commonly used to charge conductors. And the way this method works is that it works by simply bringing two conductors to contact, and they will get charged immediately. Let's look at an example here. If I have a piece of aluminum, so let's say I have an aluminum foil previously charged with a negative charge. If I bring it towards a neutral sphere, this sphere should be put on an insulating stand. So this is a neutral sphere, this is an insulating stand. If I do this, then I bring the two objects in contact. So if I bring the two objects in contact, basically what will happen is that at the end of the experiment, oops, let me draw this here. So I have the aluminum foil and the neutral sphere in contact. The charges are going to distribute themselves between the aluminum foil and the neutral sphere, and in the end I'll have the aluminum foil and the neutral sphere independently, each of them having negative charges in it. So this method is called charging by contact. It is a very quick and easy method for charging conducting materials. Obviously, this method cannot be used to charge insulators because insulators cannot transmit the charge even after contact. Let me go ahead and look at the third method of charging, and that's going to be charging by induction. Charging by induction. So the method of charging by induction is used, I should say this method is used to charge conductors without physical contact between these two conductors like it is in the previous method. So the method of charging by induction is used to charge two conductors without their physical contact. Let us look at some examples of charging by induction. Examples of charging by induction. The first example we'll look at is charging a sphere conducting sphere. Let's charge it positively by induction. Charging a conducting sphere positively by induction. Remember, this method does not involve any physical contact. So the first step, okay, use a better color. The first step is to have our insulator, our conducting sphere, put perfectly on an insulating stand. Put it on an insulating stand for obvious reasons. If this sphere is made to touch the earth, then it will always be at zero potential and it cannot be charged. So here we have our neutral sphere. It's a conducting sphere, it does not have any charge. In the next step, since we want to charge the sphere positively, we are going to bring a negative charge towards it. So there is my conducting sphere. So I bring a negatively charged body It could be a piece of wood or a piece of rubber. I bring it near here. So Remember, for a neutral sphere, this basically means there is an equal number of opposite charges, so an equal number of positive and negative charges. So basically, these charges that were initially neutralizing each other will now redistribute themselves due to the presence of a negative charge. So positive charges will align themselves close to the negative charges because of the fundamental law of charges, that like charges attract, unlike charges attract. So negative attracts the positive, while the negative charges will be repelled. It's important to note here that the inducing charge is equal to the induced the inducing charge is equal to the induced charge. So I have the same number of charges here as they are in the inducing charge. Basically, there will be almost an infinite number of charges here, so we only have to make sure that the inducing charge is equal to the induced charge. That's my second step in the process. The third step in the process, while keeping the negatively charged object in place, so I'm going to earth the sphere. So I'm going to connect the sphere to the earth. This symbol here means earth or ground. Basically, the earth or the ground has plenty of charges. It has both positive and negative charges. We say it is at zero potential, so it can contribute any charge that we need. In this case, all the electrons are going to be drawn because they are not being held by any charge here, while the positive charge is bound to stay here as long as the negative body is still in place. And lastly, the negative body is then removed, and after it is removed, the positive charge will redistribute itself in the sphere, and now the sphere has a net positive charge. These steps are very critical. If we take away the negative body while connecting the sphere to the earth, then the sphere will not be charged. We have to make sure this body remains in place while we are earthing our sphere. Let's make this more interesting by charging two spheres oppositely. So our second exploration here. Let us charge two spheres. Charging two spheres oppositely at the same time. So the first step is to have our two spheres. We have to make sure they are insulated from the ground. They are metallic spheres because they are conducting. The second part, while these spheres are in contact, we bring a charged body here. It could be positive or negative. Let's suppose that this body is positively charged. If this body is positively charged, because the two spheres are in contact, they will behave as though they are all a single metallic sphere. So negative charges will be attracted to this end and positive charges will be repelled to the other end, because positive attracts negative but positive repels positive. So this is a positively charged body. Positively charged body. We could also do this with a negatively charged body. This would be positive, this would be negative, same thing. Okay, the third step, we have to make sure that this remains in place, and while it remains in place, we separate the two spheres So we separate the two spheres. This one remains with a negative charge, this one remains with a positive charge, and lastly we take away the charged body, and our spheres will not lose their charge in this case, because they were separated while the inducing charge was still in place. Still, step number C is very important, because if we take away the charged body before separating the spheres, then we will not have the process work very well. In fact, the spheres will not get charged. If the charged body is taken, these charges will immediately cancel out quickly, and so we will not have any charge on them, and they will become neutral again. Okay, let's have another interesting example of charging spheres by induction. In this example, we are going to charge two spheres, charging two spheres. Okay, the previous example, we charged them oppositely. One became positive and another became negative. In this example, let's charge the two spheres simultaneously at the same time, so that they obtain the same charge. Let's say they obtain a negative charge. Okay, let's just take this for exploration. So the first step is to have our spheres well insulated and separated. Okay, very important. Then we bring, since we want to charge them so that they get a negative charge, we have to bring a positively charged body. Positively charged body. For example, a glass rod that is rubbed with silk. The second step, okay, shouldn't have done this at this step. So we have our two spheres that are insulated from the earth. Since we want to have them become negatively charged, at the second step I will introduce the charged object. So there we go with our positively charged object. When I bring the positively charged object, this part will become negative. This part will also become negative, because the positive charge attracts the negative charges in every sphere, and the positives are going to be repelled to the far end. In the third step, I keep the positive body in place. Keep the positive body in place. I only do a simple modification here. This is negative, positive, negative, positive. So with the positively charged body still in place, I connect the spheres to the earth. and basically electrons will move upwards to neutralize. Electrons are negatively charged, so they would move upwards to neutralize the positive charges. Remember, protons do not move, only electrons can move, so electrons would move to neutralize the positive charges. And lastly, I can remove the earthing and the positively charged body, and I will end up with two spheres that are negatively charged. And there we go. So we can do a lot of other interesting stuff with charging by induction. You can try playing around with others. You can try doing all these examples again, but with opposite charges. Okay, let us conclude this part by looking at polarization. And this mainly happens in insulators. So let's say polarization in insulators. So polarization is the displacement of the centers of positive and negative charges, the displacement of the positive and negative charges in an atom when placed in an electric field. We'll see what that is in a moment. When placed in an electric field. So we all know that for a normal atom, the protons are at the center and the electrons are in a cloud around the nucleus. So this is a normal atom, but for a polarized atom, if I have my atom and I place it in an electric field, okay, so we have an electric field. This means there is an electric force acting in this direction. The positive charges are moving in this direction. This is what happens. The nucleus will remain at the center because it does not usually move, or at least it will be slightly displaced, but in most cases it will remain at the center only with a slight displacement, and most of the electrons are going to be shifted to this side. So as you can compare the two atoms, in the polarized atom, the center of the negative charges has shifted towards this side because there's an electric field acting in that direction. Also, you can see the shape changes from being a regular circular shape, from a regular shape to an oval shape that illustrates polarization. The negative charges have shifted to one side and the positive charges have shifted to the other side, and in that case we say the atom is polarized. So let's look at a broad view of polarization in insulators. Let's look at polarization in a broad sense in insulators. Suppose we have, suppose we place an insulator in an electric field. Suppose we place an insulator in an electric field. So the electric field is in this direction. This is our insulator. This is the electric field. This is the insulator. Basically, this insulator has many atoms in it. Maybe I could show a before and after picture here. This is what our insulator looks like originally, so without field. This is no electric field. In this case, all the atoms are well aligned. So these are the atoms in our insulating material. These atoms are unpolarized. This is our insulating material. So the positive charge is at the center originally, and the electron cloud is surrounding the atom as it should for a normal atom. But what happens after an electric field has been applied is that the shape of the atoms is going to change. So these are polarized atoms now. As you can notice, their shape changes. I'll only draw a few. Their shape changes. Since the electric field is in this direction, the negatives will all go to this side and the positives will go to the other side. Okay. Positive, minus, positive, minus, positive, negative, positive, negative, negative, positive, negative, positive. So as you can see, these are now polarized atoms. These are polarized atoms. Also, notice from this diagram that the positives and the negatives in this case are going to neutralize. Also here, the positives and the negatives here are going to neutralize. So the final effect will look like this. Okay. Finally, our insulating material would look like this. This side is going to be negatively charged and this side is going to be positively charged. So it is as if induction has occurred inside the insulating material. So virtually this is not induction, it is called polarization, and this would be what we would somehow call induction in insulators, but it has a specific name called polarization. So this one here is now a polarized insulator, and because this insulator is polarized, if we bring a charged object, so if we bring, let's suppose, if we bring a charged object towards a polarized insulator, this polarized insulator, it's very important to see here that it was originally neutral. So if we bring a charged object towards a polarized insulator, then there will be attraction. And this explains why neutral bodies are attracted by charged bodies, because of the process of polarization. I'll show you an example in a moment. As you can see in this diagram, in this picture, okay, now, so in this picture, as you can see, the pieces of paper are being attracted by the comb. These pieces of paper are insulators and they are originally uncharged, but when a positively charged comb, after rubbing it with hair, when it is brought to the papers, they are able to be attracted. Let's see how this happens. So we have a comb. Okay, hope that works. My comb is bad. Okay, this comb is having positive charges on it. Let's say it has positive charges on it. And then this is the piece of paper. This is the piece of paper. So what happens is that because of the positively charged comb, this part is going to become negative and this part is going to become positive. That is something called polarization. We have just seen how this happens. And because the positive charges and the negative charges attract each other, because these two charges are near than the distance between the positive and positive, there is going to be greater attraction, and so the neutral paper is going to be attracted by the positively charged comb by this process of polarization. So this is a very important phenomenon, and you should also perhaps read about more interesting stuff in polarization, like polar molecules. Molecules such as those of water and hydrogen chloride have some natural degree of polarity, so they can easily be polarized to a higher extent. Thanks for watching this episode. Next we'll look at the gold leaf electroscope.